Okay. All right. It's week 4 Wednesday. That's a typo. And we will continue talking about NumPy. So NumPy is the kind of the library or the module that you would load into Python that that allows for these array structures, these NumPy arrays, which is very similar to an R vector and an R matrix in that all of the values inside the array have to be of the same data type. And the advantage of this is that, you know, when you see an array, you can kind of expect what kind of values will appear, and it greatly speeds up any kind of numeric calculations. So NumPy is actually very fast, even for very large arrays and things of that nature. And, you know, a lot of kind of advanced, a lot of these packages such as, you know, scikit-learn and, you know, PyTorch, which do, you know, neural networks in Python and things of that nature, are underlying rely on NumPy arrays for its to power them. And so, you know, on Monday's lecture, we talked a lot about just kind of creating arrays and reshaping them, and, you know, we saw some of the properties there. Just wanted to cover a little bit more about the other things that you can do with arrays. So a lot of times you need to kind of join arrays together, and that's called concatenating them. So here I have two one-dimensional arrays. So these are one-dimensional length 4 arrays. I've got X, which is 0, 1, 2, 3, and Y, which is 100 through 103. And we can concatenate these in a couple different ways, right? So if you just do concatenate XY, and you can provide it a list or tuple of the objects that you want to concatenate, it's going to just kind of append them together. So these are one-dimensional arrays, and so there's just one direction or one dimension upon which you can concatenate. And so these, you know, X is originally a length 4, a one-dimensional array, and after you concatenate X and Y, it becomes a length 8 one-dimensional array. All right. You can say, I want to concatenate along the index 0 axis. All right. And so, you know, if we asked, you know, what is the shape of X, we would get a tuple, a length 1 tuple, and it would just say 4 comma to indicate that it's a length 1 tuple. And so, you know, that's the 0 indexed axis. And so again, you know, you can say concatenate along axis 0. Now, if I specify I want to concatenate X and Y together along axis 1, okay, which would, if this was a, you know, a 1 by 4, we would be able to do that. But here, trying to specify axis 1 as in, you know, stack the X on top of the Y, if I were to try to do that, it throws an error, okay? And the reason why is because X is one-dimensional, and so there is no axis 1. Remember the shape of X. So if I were to ask, what is the shape of X? The shape of X, you know, X dot shape would be something like 4 comma this, right? And so here we have index 0, axis 0 is length 4, and there's no axis 1. So it can't do that, right? X shape and Y shape both have this. All right. So again, that's the X shape. So you can do something called VStack. VStack will take X and Y, and it will stack these on top of this, right? The other option you can do is you can reshape X into, you know, if you reshape X into having dimensions 1 comma 4, then you could also concatenate along axis 1. So VStack will stack them vertically and create this, right? The other option, again, is we can turn X into a 2-dimensional array, right? And so this is a 2-dimensional, and again, we can tell that we can distinguish, just from printing out, we can distinguish between X when we print out, looks like this, okay? There's only one opening bracket, okay, which indicates that it's a one-dimensional array. versus over here, there's 2 opening square brackets, which indicates that it's a 2-dimensional array, right? And so, they both kind of look like these row vectors, but this one is a 2-dimensional array with shape 1, 4, right? It's got 1 row and 4 columns. And here I'm going to take y and I'm going to reshape it to 1, 4. And now I can concatenate along axis 0. Okay, so along axis 0 is concatenate them along the rows. All right, or so you're going to basically, so we are going to basically paste this on top of this. Axis 0 means take the first axis 1 and 1 and combine them, and so the result is going to be 2 by 4, right? Because the first axis or the first dimension is the row, and then the second is the column. So that's axis 0. And if I do axis 1, basically it's saying the result, all right, is going to be 1 row, and we are concatenate the second dimension, which is currently 4 and 4, and so the result is going to be 1 by 8. Does that kind of make sense? Y axis 0 here ends up being a 2 by 4 matrix, and concatenating along axis 1 ends up being a 1 by 8 matrix, or a 1 by 8 array. I just kind of want to make sure that this is okay. Just because it feels, it feels a little bit strange that back here when I said concatenate along axis 0, it ended up being length 8. Okay, but that's because this is a 1-dimensional thing. All right, and so over here when I say axis 0, because the first dimension is the rows and I concatenate along that, we're going to end up having 2 rows. When concatenating 2 rows. Okay, so here is I've got 2 matrices now, 2 arrays. All right, X matrix, that's what XM is supposed to stand for, is a 2 by 3 matrix. Okay, 0, 1, 2, 3, 4, 5. And then YM is another 2 by 3 matrix, 2 rows, 3 columns, 100 through 105. All right. All right, so if we ask what's the shape, XM and YM are both 2 by 3s, and that's fine. All right, and so now we can concatenate, and the default behavior of concatenate is to concatenate on axis 0. So in our case, axis 0 is the number of rows, and so if we concatenate across rows, and if I sum 2 and 2, I would get 4. So the resulting shape is going to be 4 by 3. Oh, you know what? Let me change this to that. Okay. So we had a question in the chat. So would a 2-dimensional array have axis 0 and axis 1? Yes. Yeah, a 2-dimensional array has axis 0 and axis 1. Axis 0 is rows and axis 1 is columns. So the way Python goes is axis 0 is rows, axis 2 is columns if it's 2-dimensional, and if it's 3-dimensional, axis 0 is the number of layers or sheets. The second would be rows, and then the last would be columns. Okay. Here, again, I'm concatenating along axis 0, and it does the exact same thing. All right, and that's same as the default because we're doing that. If I say along axis 1 is concatenating along the columns, and so the originals are 2 by 3 and 2 by 3, and so the result is going to end up looking like this. Okay, so XM is over this 2 by 3, and the YM is this 2 by 3. And they get concatenated along the columns. Okay, and similarly, you can do VStack and HStack, which is very similar to concatenate, except VStack stacks them vertically, and HStack stacks them horizontally. Okay, and these are for kind of 2-dimensional structures, but you can also do them with 1-dimensional structure, and it will kind of turn them into 2-dimensional structures. All right, so we like NumPy. Well, actually, before I get into that, let me give you your first view quiz answer. So for 4th week Wednesday, first view quiz answer is B. B as in bear. B as in bear is your first view quiz answer for today. So jot that down. B as in bear. Okay, so let's say we want to just do some math operations. And so this, I think, works entirely as you would expect and predict. And so here, if you say take X and add 5, it's going to take your array X, and it's going to add 5 to all elements. And so we get 5, 5, 6, 7, 8. You can take X and add Y. You have these two things and you add them together. And it's going to do element-wise addition. So we get 100, 102, 104, 106 when we add 3 and 103 together. X times Y. So regular, just the star is going to do element-wise multiplication. And so, 0 times 100 is 100, 1 times 101 is 101, 2 times 102 is 204, and 3 times 103 is 309, all right? And then, if you wanted to, you can call sum on any kind of array. And so the result of this, if you add all of these up, you'll get 614. All right. You don't have to do element-wise multiplication. You can do what's known as the dot product. So you can treat these as kind of like vectors. And the dot product is much like doing element-wise multiplication and then calling the sum, right? So you're basically, when you do the dot product, you're multiplying the first elements together and then adding them to the second elements multiplied together and so on and so forth. So you can do np dot dot and it will do that. Okay. And then if you call the at operator, is pretty much performing a dot product if you provide it basically one-dimensional vectors. So one-dimensional vectors will basically do a dot product between X and Y as well. And there's actually one more that you can do. You can call X dot dot Y, and it will perform the same thing here. Okay. And notice this function is called you call it by calling np numpy dot dot. So this is a function that exists within the NumPy module once you load it. All right. Again, here are, I have two matrices here. So instead of one-dimensional arrays, now we're looking at these two-dimensional arrays. So these are two 2x3 arrays. And the behavior is, again, exactly as you would expect. So if you take a two-dimensional array and add a constant, it's going to add the constant to all of the elements. If you were to multiply it by a constant, it would do that as well. If you take two arrays that are of the same shape, then it will do element-wise addition, right? And so if you give it another array that's of a different shape, it's going to complain or it's going to error out. But here we've got compatible dimensions, and so we can do that. And so 0, 1, 2. 0, 1, 2, 3, 4, 5 is your X matrix, and your Y matrix is 100 through 105. And so you get, added together, you get 100 through 110. Right. Again, just so you can see what is happening with XM and YM, I can do element-wise multiplication. And again, 0 times 100 will give me 0, and 5 times 105 will give me 525. So this is just element-wise multiplication. You can also call dot multiply. Okay, so dot multiply is a lot like, is basically doing this, but you can kind of specify the function this way as well, and this will perform element-wise multiplication as well. Okay. And all of these, again, I left off. The third way is you can call the method from the array itself, right? So the alternative to element-wise multiplication is to do matrix multiplication. And so if you wanted to do matrix multiplication, you can do that as well. And so in order to kind of make these compatible, I would have to do X matrix multiplied by Y transpose, right? And so because X is a 2x3 and Y is a 2x3. And so if I transpose Y, I would get a 3x2. So 2x3 times a 3x2 can be multiplied. And so I can do numpy dot dot, and this would perform matrix multiplication. So 2x3 times a 3x2 will result in a 2 by 2, okay? And that, it performs exactly kind of what you would expect. So if I transpose this, then we're going to have 0 times 100, 1 times 101, and 2 times 102, and those would get added together. So 204 and 101 would add up to 305. And then similarly, we would do the same for these ones, and we get 314, and so on and so forth. Okay. The other ways we could call this is you could, and so this is, I should have written these. You know what, I'll go back and do that in a moment. You can do XM, you can take the matrix itself, XM, and you can call the dot method, okay? And you can say XM multiplied by YM transpose, and we're gonna get the exact same result. And then lastly, you can use the at operator, which performs matrix multiplication. So this is kind of the equivalent of R's percent star percent operator. The at operator performs matrix multiplication. And so we get the same result here. Let me just go back and fix up a couple of things here. So I can also do element-wise addition, element-wise multiplication. And so another version of this would have been xm dot multiply ym. Whoops. Did that not work? xm. Oh, never mind. I cannot do it. I am mistaken. Okay. Never mind. Okay. I guess it only has dot dot. It doesn't have dot multiply. Okay. So we have that. All right. Other things you can do. So this is, addition, subtraction, element-wise multiplication. This is all expected. 0, 1, 2, 3 plus 4 minus 5 times 2. All right. The division always results in a float. Okay, whereas these ones, because I'm just kind of adding an integer. So this is an array of integers. I'm adding integers. These remain integers. I'm subtracting an integer. They remain integers. I'm multiplying by an integer. Everything remains an integer. Over here, once I do division, everything turns into a float. Okay, you can take the negative of some matrix with the negative sign. And then you can do powers, all right? So powers there. And you can do modular division, and you can also do integer division, which I did not include. And then you can also call the absolute value function on an array, all right? Although it's a little bit silly here because everything is positive already. Okay, there are, so trig functions are not part of base Python. And so if you want to run a trig function, you can call, you can load the math function, or there's also trig functions as part of NumPy, all right? And in general, if you're using NumPy arrays and you want to do any kind of math operation, such as, trig functions or exponentials or logarithms, generally it's recommended to use the NumPy version of the functions, because a lot of times some of these things are internally optimized to perform faster and better with NumPy arrays. Okay, whereas the base math library is adequate, but some of them might not have the same optimizations. In some cases, the operations don't really make a difference in terms of performance, but in general, the NumPy ones will be internally optimized to perform better on these kinds of NumPy arrays. Okay, so anyway, I'm going to create a NumPy array going from 0 to pi, but we want them linearly spaced. So we're going to have 0, 1/4 pi, 1/2 pi, 3/4 pi, and pi. Okay, or at least some decimal approximation of it. And then so if I call sign on it, I get 0, I get square root of 2, 1, square root of 2, and 0, right? And so, I think by now you're accustomed to recognizing that this represents 0 whenever you see something And anytime you see 10 to the negative 16, something along that order, that's pretty much like the limit of, this is pretty much close to machine epsilon here. And so this is pretty much 0 as far as we're concerned numerically. Okay, and then, as far as cosine goes, we get 1, square root of 2, 0, negative square root of 2, and negative 1. Okay, and again, this is 0, 10 to the negative 17 there, right? And then as far as if we do tangents, we would get 0, 1. This is, I guess, infinity, okay? 10 to the positive 16, that's a far cry from infinity, but, it's kind of approaching a big number, right? And then we have negative 1, and then, something along the lines of negative infinity, right? Okay. And then again, log and exponent functions here. So dot log will be your natural log ln, and then log 10 will be your base 10 log, okay? And so, so you have that. So this is just, I'm making, 1, 10, 100. And so if you do log base 10, you get 0, 1, 2, and so on and so forth. And then the exponential function is .exp, np.exp, and that works just fine. 1, e to the 2, e to the 3, e to the 0, 1, and 2. Okay. And then exp2, this is 2 to the y. Okay, and so to the 0, 1, and 2 will give you 1, 2, 4, so on and so forth. You can also call np.power, and whatever this is you specify some constant here. So in our case, I just did 3. And so, 3 to the first power, 3 squared, so on and so forth. Okay, you can use sum, and there's the built-in Python sum, and there's numpy's .sum. Okay, numpy.sum is generally much faster, and it actually works different from the regular old sum. Okay, so if you just have a single one-dimensional array, they're gonna work the same, right? So if I do 0 through 99, and I say, add them all up, we're gonna get 4950. Okay, and then you can also call np.sum, and if it's in a one-dimensional structure, we get exactly the same results. Okay, so for these arrays, we get the exact same results for these one-dimensional structures. Okay, when you have two-dimensional structures, however, let me so suppose you do from numpy import sum. Will Python get confused which sum to use? Well, it's going to use the numpy sum. If you do that from Python import sum, it's whatever you import, it's going to get put into kind of your local, as far as the scoping rules go. If you say from some package import this function, that's the name that will appear kind of in the hierarchy of things. That's going to get loaded into kind of your local environment. So that name will take precedent over the built-ins. Okay, so if there's like multiple things, right? So if you say from numpy import, let's say sign, and then you say from math import sign, okay, whichever one you do last is the one that's going to take precedence as far as typing out your name. Okay, so there's also a big performance difference between NumPy and NumPy's sum function and Python's base sum function. Okay, and so here I created just this huge array, 10,000, I guess 10, I don't know how big that is. Okay, 10,000, and we say, do it, and we're going to call sum, and we're going to call np.sum. Jupyter has these built-in timing functions. Okay, if you call the time it's going to run a whole bunch of loops, and it's going to time how long each of these loops, each of these operations. It's going to run this operation, and it's going to do it like 1,000 times, or in this case, it did it 100,000 times. And so if you run a percent time it'll might take like 30 seconds for it to run, and it's going to just time how long it takes. and then it will report back. Okay, and so what you can see is just a huge performance difference. Here it says, to add up 10,000 numbers, 10,000 random numbers, Python, I'm sorry, not Python, the regular sum function, the base Python sum function took about 1.58 milliseconds, plus or minus 15.3 microseconds per loop. And then over here, np.sum, the NumPy sum function, took 5.44 microseconds, okay, at least on my machine. And so this is, what is this? Milliseconds and 5 microseconds. So this is on the order of around 200 times faster, 200 times, 200 times faster than the other, okay? Oh, maybe even close to 300 times faster than the other function, okay? Right, so what is 1.58 divided by 0.00544? Yeah, 290 times. The other one took 290 times longer. Okay, so it's a lot faster. Similarly, we can also call min and max on the thing. And so, in our big array, which was 10,000 values, we can say, what was the smallest number it encountered, right? And so it says, you encountered 6.5 times 10 to the negative 5, and the biggest number was 0.99998, okay? And so, these two functions, min and np.min and max and np.max, they end up in the same result. But as far as how fast it takes, NumPy is just much, much faster. So if I do 970 divided by 4.22, around 230 times faster, okay? So it's just much faster to use these NumPy functions, right? Okay, you can also call these similar functions, the sum and min and max and stuff, and you can call them on matrices, but you're going to get different results from using the base sum function versus the NumPy sum function. Okay, so here I've got a 3x4 matrix. Okay, and I just took the integers 0 through 11 and just rearranged them randomly. I just shuffled them around. Okay, so I shuffled them around, and this is what I got. And if you call sum using base Python's sum function, for some reason, it decides to sum them down the columns. Okay, I'm not sure the reasoning in terms of the the design decision why they chose to do it this way. But this is the behavior of the sum function in base Python when you give it a two-dimensional array. Okay, and I think what it is it internally it's stored. I'm not sure. Okay, but anyway, you can see we get sums across the columns: 2, 1, 11 add up to 14, 3, 6, and 9 add up to 18, so on and so forth. Whereas NumPy.sum, I think, makes a lot more sense, and it just adds up all the numbers together and gives you a single value, 66. Okay, so I'm not quite sure the design decision behind this behavior, but anyway, I think I would recommend NumPy.sum. Okay, if you want this, you can still get it. Okay, you can ask NumPy, and you can ask for sums across the column sums and things like that. Okay, so again, here is our matrix M. All right, and here we're going to say sum axis 0. We're going to say take the matrix M and sum on axis 0, and that basically means collapse axis 0. So axis 0 is the rows, right? So we have our shape is 3 by 4. Okay, and so when you say axis equals 0, it basically means collapse axis 0 down to 1, right? Because when you ask for a summary function, like what is the sum, what's the mean, what's the standard deviation, you're taking basically a vector or an array of numbers and you're collapsing it down to one number, right? So here we're going to say take axis 0 and collapse axis 0 to 1, and so we're going to get four values, right? We're going to get the column sums. Does that make sense as far as specifying axis 0? because sometimes people say, well, I said x is 0, so I'm expecting to get 3 numbers because there's 3 rows, okay? But here, when you say, when you specify the axis, you're basically specifying which axis to collapse. You're saying sum over the rows, okay? And so you're going to end up getting column totals, okay? If we say axis equals 1, we're going to say collapse the columns down to 1 column. And so you're going to end up getting 1 column, which means you're going to have 3 numbers. So you're going to get, if you add these up, 2, 3, 4, and 10, you get 19. 1, 6, and 7 adds up to 1, 6, 0, 7 adds up to 14. 11, 9, 8, and 5 add up to 33. You can also, you don't have to call sum, you can call any of these other summary functions, min, max, whatever. And so if I say min across axis 0, okay, so collapse axis 0 and find the min, it's going to find the minimum of this first column, which is 1. It's going to find the minimum of this next column, which is 3, the minimum of the next column, which is 0, and the minimum of the last column, which is 5. That's what we get. You can also ask for things like the standard deviation and the mean, all right? And so if you just do np.standard deviation, it's going to take the standard deviation of the entire matrix, of the entire array of values, and it will just return 1 standard deviation. Here, if I say axis equals 0, it's going to collapse the rows down to basically 1 row, and we're going to have just 4 numbers. And it's going to be the standard deviation of this, of 2, 1, and 11 is this. The standard deviation of 3, 6, and 9 is this. The standard deviation of 4, 0, 8 is this. The standard deviation of 5, 7, 10 is this, okay? Similarly, you can ask for the mean, all right? Mean with axis 1 will result in 3 numbers. The mean of this, the mean of this, the mean of 1, 6, 0, and 7 is 3.5. The mean of 11, 9, 8, and 5 is 8.25. Okay, is that good with everybody? As far as how these summary functions work and how the axis specification goes there. Okay, let me go ahead and give you your second quiz answer. Second view quiz answer is D. D as in dog. D as in dog is your second view quiz answer for today. Okay, same kind of idea happens in higher dimensional arrays. Okay, so here I've created a array with 2 sheets, 3 rows, 4 columns. Okay, so this is a 2 by 3 by 4 array. All right, and here, just to kind of simplify, I just put everything into ones, as I called np.ones, 2, 3, and 4. And so if I call sum on axis 0, all right, so we want to kind of collapse our sheets down to just 1 sheet. We're going to get all of these ones will become 2, 2, 2, 2, 2, right? This, if I say sum across the rows, basically we're going to collapse down the rows, right? So here we have a total of 3 rows, and so basically this will get collapsed down into all of these rows will get collapsed into 1. So we're going to end up with a whole bunch of 3s here. Okay, and the last one, oh, it got cut off. But if I say collapse across axis 2, axis index 2, I've got 4 columns here, and so the resulting structure is going to be a 3 by is it 3 by 2? No, it's going to be 2 by 3. It's going to be a 2 by 3 structure, okay? Because we're collapsing this, we're going to have a 2 by 3 structure, and the sum is the values are going to be 4 across all of those things, right? So basically, I'm collapsing this. When I did axis 0, I'm collapsing the 2 down to 1, and so the resulting structure is going to be 3 by 4. When I say axis 1, I'm collapsing this index 1 down to 1 thing, and so the resulting structure is going to be 2 by 4. And then the last one, I'm collapsing axis 2, or summing across axis 2, and so the resulting structure is going to be 2 by 3. All right. In NumPy, the way we specify kind of missing values is by using nan. Okay, so nan is a floating type number, and you can create nan directly by calling x equal to float nan. All right, and so if you just do quote nan, it's going to treat it as a string, but if you do float, on nan, it's going to create a nan type or a nan value, and that's a class float thing. Okay, you can also create nan indirectly because you will get the result of nan from these kinds of calculations. So floating point numbers, can store not a number. They can also store infinity. And so if you try to do something like infinity divided by infinity, that results in not a number. Infinity minus infinity results in not a number, and things like that. Okay, so anyway, if you say, I want to calculate the sum of not a number with a number 2, right? So here I just have this I created a list, and I say take not a number and add it to the number 2. It's going to say, I can't do that. That's going to result in a nan. Okay, but you have basically the nan-safe version of sum. So this is kind of like in R, you can say sum with na.rm equals true, where it's basically going to ignore any kind of nan values or missing values. And so here you can say nan sum, and basically it's just going to ignore anything that's a nan, it's going to ignore, and then it's going to give you the sum of everything else. All right, so here is the sum of the remaining numbers, which is just 2, and so your result is just going to be 2.0. Okay, and so so that's going to basically all of these functions have a nan version that that will work. Okay, so you have sum and nan sum. You can take the product. So these are all kind of summary functions that will take an array of values and collapse them into one, or unless you specify an axis. So sum, product, mean, standard deviation, variance, min, max, argmin, argmax, median, and percentile will all kind of, well, okay, percentile will give you one result summary value back, but you kind of have to specify more arguments here. But it's going to just kind of do all of these things, and you have the nan version, which is basically the exact same name with just a nan in front of it, and that just means ignore the nans. So it doesn't treat nans as zeros or anything like that. It just ignores them completely, which may or may not be what you want, depending on your thing. Okay, NumPy does this thing called broadcasting, and this is it's a very useful and handy thing, but it's also a little bit hard to get your mind around until you use it a bunch of times. In the beginning, it just seems a little bit like a mystery, or at least it just feels a little bit strange until you do it a whole bunch of times, and then you get used to the kind of this idea of broadcasting. Okay, so basically, if you have two arrays that are of the same shape, you can add them together. And then if you try to add something that's of a different shape, so A and B are both one-dimensional arrays of length 3, and I can add those two together. Here, C is a one-dimensional array of length 2, and I can't add that to C. Okay, so I can't add A and C together because this is only length 2 and this is length 3. So NumPy comes back and it says, no, you can't do this. All right. But what you can do is, if you have some compatible shapes, okay, there's something called broadcasting, which is similar to the idea of recycling in R, except it's a little bit different as well. Okay, so here what we have, A is a one-dimensional vector or one-dimensional array, length 3. E is a two-dimensional array, 3 by 3. Okay, 3 by 3. And I can say, well, can you take E and add A to it? All right. And what NumPy does is it takes this 1, 2, 3, and then it broadcasts it, meaning it's going to take it and it's going to kind of duplicate the rows so that it creates a matrix of compatible shape, which is going to basically be a 3 by 3 matrix with the rows 1, 2, 3, 1, 2, 3, 1, 2, 3, and then it's going to add it to E, and so you get 2, 3, 4, 2, 3, 4, 2, 3, 4. Right? I think that's not a surprise. That sounds reasonable. Okay. Here, if I take A and I reshape it to be a 3 by 1, okay, and I say take E and add A to it, okay, it's going to take this and it's going to broadcast it. So you have columns a 3 by 3 that goes 1, 1, 1, 2, 2, 2, 3, 3, 3. And then when you add it to E, which is all ones, you get 2, 2, 2, 3, 3, 3, 4, 4, 4. Okay. That is straightforward, I think. Okay. Here, I've got a 2 by 3 matrix. A is a one-dimensional array of length 3. And I can do, I can say take D and add A to it. And we get this. We get 2, 4, 6, 5, 7, 9. We're going to add 1, 2, 3 to this, to the 1, 2, 3. I get 2, 4, 6. 1, 2, 3 to the 4, 5, 6. And I get 5, 7, 9. Okay. That sounds reasonable. Okay. Here is D. D is 1, 2, 3, 4, 5, 6. And here C is a one-dimensional matrix or one-dimensional array of length 2. And if I say take D and add them together, NumPy says, no, I can't do that, right? Because what it's trying to do is it's trying to add the 7 and 8 to this. And it says, we're running into some problems here, okay? But what we can do is we can reshape C to be a 2 by 1, okay? If I reshape C to be a 2 by 1, then it has no problem. It's going to add the 7 to here and the 8 to here, and we're going to get 8 and 12. It adds the 7 to the 2 and the 8 to the 5, and we get 9 and 13. The 7 to the 3 and the 8 to the 6, and we get 10 and 14, right? So if I basically, I can't call transpose directly on C, right? Because C is a one-dimensional thing. And so if you call transpose on it, it's still going to be one-dimensional, okay? But if I can reshape it to be a two-dimensional thing where we have 2 rows and 1 column, and now we can broadcast the matrix. Okay, this is where broadcasting gets seems a little bit magical. Okay, I have two matrices. Okay, E is a 10 by 1, 10 rows, 1 column. F is just an array. Okay, F is an array, a one-dimensional array of length 11. Okay, I can add these two together. I can do E plus F, and you say, well, how is that even possible, right? So here's a 10 by 1, and here I have a length 11 one-dimensional thing. Okay, so what happens is NumPy looks at E and F, and it says, okay, can I broadcast E to be something in the shape that's going to be compatible with F? Okay, and it's actually going to broadcast both of them to something compatible. And it says, okay, what we can do, well, F is length 11. So what we're going to do is we're going to take E and we're going to just broadcast. So it becomes 10 rows, 11 columns. Okay, and it's going to take F and it's going to broadcast so that it's going to be 10 rows, 11 columns. And the result now is a matrix that's 10 rows and 11 columns. So it takes E and it broadcasts it to be 10 by 11. It takes F and it broadcasts it to be 10 by 11. And it produces this result here. Similarly, you can do it with multiplication. So same thing, whether it's addition or multiplication. And so if you do multiplication, you basically get your times table that, I don't know, I imagine you guys had to make one of these when you were in like 2nd or 3rd grade. You had to create your times table, and you know, it's done with a line here in Python, and you get your multiplication tables, right? 8 times 9 is 72. You know, this is your squares and stuff like that. Okay. Okay. What is happening with this? All right. So here with D, I have a 2 by 3 thing, and what I'm going to do is I'm going to reshape it to be 1 by 6. I'm going to reshape D to be 6 by 1. And again, NumPy is going to look at this and it's going to say, okay, the shape here is a 1 by 6 row matrix. Okay, a matrix 1 row 6 columns. Here, this is a matrix 6 rows 1 column, and then it broadcasts them both to be something compatible, which is going to be a 6 by 6. ooh, we're going to run out of time here. Let me just kind of go through this quickly. All right, so that's broadcasting. Okay, NumPy also will result, can produce kind of Boolean values. All right, so here is just, here's an array that goes from 0 through 5. You can just do simple comparisons, and you can say what values of x are less than 3, and you're going to get true and false values. Okay, so it's, you know, these are true, these are false for being less than 3. Greater than or equal to is, you know, complement of this, things like that. Which ones are equal to 3? Okay. You can also take those. You can take a vector of trues and falses and use that to subset, you know, any other kind of matrix of the same shape, right? So we can say subset X based on what values are greater than or equal to 3, and we get this result, okay? And we can also call, you know, sum the values of X greater than or equal to 3. Now remember this thing, X greater than, not sum the values that are X greater than 3, it's sum the Boolean values, okay? So X greater than 3, falses get turned into zeros, trues get turned into 1. And so the sum of that array of Boolean values will get, will add up to 3. Okay, you know, np.mean is basically going to find the proportion, right? So you got zeros and ones. What's the mean of the zeros and ones? You're going to get a proportion. So it's 50%. Okay, the tilde is going to give you the complement of any kind of Boolean thing, right? So here we can say what values are equal to 3, and then tilde is going to basically say not that. All right, so all the falses become true and the true becomes false. All right, so you can also do the same thing. This generalizes to higher dimensional structures like a matrix. We can say, all right, so here is 0 through 11, which ones are greater than or equal to 6, and you get a structure of these things. And again, you can call sum, and you can say, all right, all of these things become zeros and ones, and you can add them up, and we have 6 things that are true. Okay, and again, just like before, you can call NumPy sum with an axis thing, and you can say, all right, collapse axis 0, so that we only have basically 1 row, 4 columns, and then we'll get, you know, first column has 1 true, second column has 1 true, columns 3 and the next columns 3 and 4 have 2 true values in them. Similarly, you can call sum it across axis 1. Okay, you also have Boolean-based bitwise operations, or basically element-wise operations for Booleans, right? So if you have 2 NumPy arrays, you can ask for bitwise and, which is the ampersand. You can also ask for bitwise or, and you can ask for bitwise exclusive or. Okay. Now, generally, you know, for your flow control, don't use this. This is kind of a NumPy bitwise operator, right? So for flow control, when you want to have if statements and else statements, and you have kind of these multiple conditions, you're going to just type out the word and, A-N-D, and you're going to type out the word or, O-R, and things like that. But if you want to get, you know, it's the difference between the single ampersand and the double ampersand in R. You know, when you're dealing with, you know, these arrays, or, you know, these vectors or matrices, you often want to kind of have these element-wise results versus, you know, in if statements and else if statements, elif statements, you know, you don't want a vector of Booleans. You only want one. And so for those things, you're going to just use the regular old and the regular old word or and things like that. Okay. Negation is the same operator, so the not operator, and you also have the any and the all, which will be, you know, are any of the values true, or all of the values true, and I think that's fairly straightforward. Okay. Okay. I think my notes are good enough for me to just say look through them regarding the fancy indexing. So, you know, you can kind of say I want to subset this X array into just element index 0, element index 1, and element index 5. Okay, and it will do it like that, right? And you can also do the same thing with arrays. Okay, so here I've got some or matrices, and you can say I want to set, for this X thing, I want to select row 0, column index 2. So row 0, column index 2 will be 2. Row index 1, column index 1 will be 5. Row index 2, column index 3 will be 11. Okay, and so on and so forth. All right, and then you also have these sort operators. Maybe I should talk a little bit more about sort operators. Okay, let's call it an end here. Let me give you your last quiz answer for today. Last view quiz answer for today is C. C as in cat. C as in cat is our last view quiz answer for today. All right, we will end here and have a good evening, and we will see you guys on Friday.